Friends, this is my first video, and I have planned to start with the discussion on plane polar coordinates. Basically, how these coordinates are helping us. We can have a body which is moving in a two dimension, and body means a particle on this body is basically following a particular trajectory. So, can we handle all kind of possible trajectories, or what was the problem with the previous very well-known coordinate system that was basically the Cartesian, or if can was that handy enough to use in all complex problems? We'll see this today. So basically, this is what you know already, the Cartesian coordinate system, which is also known as a rectangular coordinate system, where what is happening, you have a particular particle's position either going horizontally or vertically. So basically, either this particular so-called particle started, which probably started from origin, keeps covering the distance along x-axis, or maybe it is covering the distance along y-axis. So whenever we try to fix the position of a particular particle, this particular particle at some time t, it is somewhere in this space. And how do we trace its position? Maybe it has reached to some distance where it has already covered some x distance, it has already covered some y distance, and likewise many possibilities are there for this particle's position. So what is happening whenever we try to trace a particular particle in two dimensional having a Cartesian system with us? So basically each time we should be ready, or we should have x and y values with respect to time known to us. So using x and y known to us with the time, we can very easily calculate its velocity, acceleration, and many other parameters. So now this is a new system, which is basically the plane polar system, where what is happening, we will not be dealing with rectangular system where only x and y are known to us. We know one more system is there available to us. What it is basically? It gives us more freedom to go in any random direction. Like for example, you see here I have drawn many circles and some arrows also. I hope you can see. So what is happening when this particle P was moving in a rectangular system? Specific points we can see where each of these points is characterized by some x value and some y value. Now here again, this particle P, I can basically take this whole circle system exactly over this rectangular one, and you can understand that tracing this particle P is more easy here. How? I mean, it can go in any random position, and each time, if I have a particular set of coordinate which can tell me the direction of this particular part, the location of this particular particle P will be easy for me. So those easy options are given through two more new coordinates now. What are those two new coordinates? One is known as the radius vector. Other one is nothing but a theta. Theta is what? Theta is the position of this particle V with respect to horizontal direction, you can say. So basically what is happening? It's very easy that can we have the relation between these two new systems, these two systems? One previously known Cartesian system, the new one is the polar one where r and theta are now coming. So the answer is yes. It's very easy. So if you see, I have drawn here the same. I have just taken as an example one particular random position particle P, which is basically at theta direction with respect to the horizontal axis. Forget about the circle, I'll discuss about it later. And then this radius vector, which is basically letting me to know the position of this particular particle P in the plane. So how do I write this R in x and y system? It's a very easy. So vector R is nothing but x I cap plus y j cap. Fine. So x and y are nothing but the intercepts of this vector r over the respective axes of x and y. So do I know intercepts? The answer is again yes. We know intercepts very well. So this vector r is nothing. I can write it like its magnitude and its direction. So what is this direction of r cap? Direction r cap. R cap is nothing but the direction of this radius vector r indicating where the r is basically directed. So r cap is nothing but the direction of the radius vector. So I will be now dealing with this modulus r. So I of course have x and y connected with r. How? See this in this triangle, we can use the cosine of the angle to give us what? The base part, which is nothing but the x, and the modulus of radius vector, which is nothing but r. So I can write x is equal to the r cos theta. Similarly, if I use the perpendicular part here, so then I can write y is equal to r sin theta. So this is how we write the two intercepts, which are basically helping us to finally write vector r. So now I have this r cos theta and r sin theta. I can definitely replace it here. So what is that radius vector have? I have basically this is r cos theta I cap plus r sin theta j cap. If I say specifically in terms of vector r and its modulus. So what is happening? We know that vector r is nothing but the product of its magnitude with its direction. So here, if I just take this product in the denominator part, so I am ready with the r cap, which is nothing but the whole expression without this r part. So this is how we know the r cap. So r cap is basically cos theta I cap plus sin theta j cap. Fine. So we also can we can very easily calculate the r cap here also in this uh, plane picture, which is basically connecting x y along with the r theta. So I have already drawn here the r cap. So r cap, if I can just take the projection I vector x is nothing but a direction I cap, and vector y is nothing but a direction j cap. So same two directions I can project here, j cap and I cap, for this so-called r cap. So r cap, using the same again triangle, we can write r cap is nothing but the cos theta component with I cap and sin theta component with j cap. So I again reach the same conclusion that r cap is equal to the cos theta I cap plus sin theta j cap. So this is how I know the direction of this new radius vector in terms of previously known Cartesian unit vectors I cap and j cap. Now here in this plane polar system, one more direction is available to us. Like in Cartesian system, we are always handling with I cap and j cap. Here also we are handling with two directions at the same time. What are those two directions? One is already known r cap, what we have already obtained. Other one is nothing but the direction of theta, where theta is changing. So if you can just look at this picture, what is happening? So in a two-dimensional plane, my particle can be anywhere. So if I talk about this radius part, so this particular direction where r is changing, and I go in the plane, all these points are letting me to get some new value of the theta. So this system, what is happening? R is changing radially, theta is changing tangentially. So do we know theta here? Theta is here already shown, and direction of this theta change is nothing but tangential, which you can see using this arrow. I have shown here theta cap. Theta cap is nothing but the direction of theta change. So what is happening? As I know already r cap in terms of theta cap, in terms of I cap and j cap, do I know the theta cap as well? So again, I will be using the same triangle where I can see that theta cap is also having its projections on I cap and j cap axes. So how do I write that? Theta cap is nothing but it's basically cos theta component with the j cap and minus of the sin theta component with I cap. How? See here, cos theta j cap, and this is reverse of the direction of the I cap, so it is basically sin theta component with I cap. So I have here now r cap and theta cap, both are known to me. I would prefer to write it here because I will be soon using them in a new form. Let me write it. Let me write it here itself. Okay, sin theta I cap with minus sign and plus cos theta j cap. And here I have cos theta I cap plus sin theta j cap. So this is how I know the r cap and theta cap. Fine. So I know the two new directions. I know the two new directions, r cap and theta cap, in terms of previously known directions, I cap and j cap. Now, do I know the? Do I have enough equations available with me to study motion of this so-called particle P in this new plane polar system? The answer is yes. Why not? How have we studied the particle P's motion in previously known Cartesian system? The way was how you were doing it. You were doing it like velocity, which is nothing but Vx I cap plus Vy j cap. So each time what you were doing basically, once using Cartesian system, your job is to study the motion of a particle P in this so-called Cartesian plane. So each time you have to basically know the component of this particle's velocity along x-axis and y-axis, and this is how you relate them. So Vx is nothing but dx by dt, very well known, means the rate at which displacement is changing along x-axis, and Vy is accordingly the rate at which displacement is changing along y-axis. So this was the way you had using Cartesian system the velocity measurements. Now how do we do it here in terms of this plane polar system? So of course I should have something analogous. So means I should have something B going along r cap, and I should again have something B going along theta cap. This is what I expect, that if I have a new system which is basically this plane polar system, so I should now have again two velocity components. One follows radially the r cap direction, other follows tangentially the theta cap direction. So let us see. So let me, for the time being, write them like Vr and V theta. No harm. So we can just indicate them. So our job is now to know what are these components, Vr and V theta. Let us try to attempt it. So basically, how do I start? Okay, I will not be needing as of now this. I would prefer to keep it somewhere so that once we are ready, we can easily relate that with what we started and where we have finally reached. So, okay. Hmm. So for this so-called particle P, which is now moving in the r theta plane, I would say, not it is not moving in the Cartesian plane. How do I write velocity? It's very so easy. Sorry, this is the rate at which this radial displacement is changing. Rate at which this radial displacement is changing. So how do I expand it further? I know that the so-called radius vector is written in terms of its magnitude and direction this way. We have already seen it here. So now let me just go on Potts differentiation. So I have it like for r cap, and again I have it for r. So basically here I have written something which can be probably new to you, that how this r cap, which is basically the direction, is now getting differentiated. Shouldn't it be a constant? So the answer, you can very easily look at the expressions what I have written here. Those can give you the clue, the hint to get the perception of the what kind of motion we are handling now. So this is the motion in this two-dimensional plane polar system where what is happening, the particle can go anywhere. Particle can go radially, particle can go tangentially, particle can go in the middle. Not necessary that it should follow the fixed radius path, not necessary that it should follow the fixed tangential path. So keeping that generalized case in the mind, what do we see? That theta may or may not depend upon time. So let me take a generalized case where theta is depending upon time. So when theta is depending upon time, so basically I say that theta is a function of time. So that would of course result that r cap would also become a function of time. R cap would also become a function of time. Again, for generalized case, I would say. We'll study the specialized case once I finish and we reach the expressions of velocity and acceleration for this particle P in this new plane polar system. So as of now, I'm having this r cap surely depending upon time. So let me now handle this expression of velocity. So okay, here no surprises because the dr by dt r cap is as it is mentioned, but here there is a something where basically I can obtain a simplified version instead of having an ambiguous situation where r cap is depending upon time, but how, I don't know. No, we know that. So let us try to simplify this r cap variation with time. So I'll be basically differentiating this expression with the time. So okay, d r cap by dt is nothing but minus of the sine theta. Theta cap, we have already mentioned that theta cap is depending upon time, so I'm taking that here. Theta dot. Theta dot is nothing but a short notation used for rate of for showing the rate of some particular parameter. Like I'll be using, or maybe I'm going to use. No, I haven't used, but this dr by dt I'll be writing it as r naught soon. R dot, sorry. So this sine theta dot, fine, and okay, and okay, cos theta dot j cap. Yes. So it is I cap and j cap. So I have now with me the rate of r cap in terms of sine theta dot I cap plus cos theta dot j cap. Now, if you see this theta cap carefully, so you would appreciate that what is happening, the theta cap is coming here. Means r cap is depending upon time and it is depending according to theta cap. So let me just write it in a simple way. So it is basically theta dot theta cap. So what is the rate of this r cap is equal to the theta dot theta cap. It's a very nice quantity and I would prefer to keep it somewhere because again this is something which I'll be using soon. So now something what is not needed I can remove as of now. So we have already seen that r cap is depending upon x and y cap in terms of unit vectors this way. So fine, this is okay. And this is how we have written the intercepts. No surprises. We have already seen that r cap and the modulus of radius vector r are related to the radius vector itself. So and this is the way we alternatively obtained the r cap, which we have already written there. So let me remove it. So now we get some space. Okay, fine. So now let me try to summarize what is this velocity I'm getting. So now I get an opportunity to write it like r dot r cap plus what is this r here? It is here r theta dot theta cap. Very interesting. situation. You recall that velocity what we expected for this particular particle P moving in a new plane of plane polar coordinate system having r and theta variables. So now we expected that whatever velocity of this particle P should be available to us should have two components, one corresponding to r cap, other one corresponding to theta cap. The same we have got. Fine. So Vr is nothing but r dot, and V theta is nothing but r theta dot. And specifically, this particular one is known as radial velocity or radial component, we can say, and this particular one is known as tangential velocity. Fine. So here itself I can finish one example, but that will be really good if I complete the acceleration part and then I show you one example of real life implementation of these velocity components. So okay, fine. So this is the velocity what I have got. Now let me handle the acceleration part. I can start here. So this is not of use now. So let me remove it. So acceleration is nothing but rate at which velocity has to change. Velocity we have got here. Let me handle this velocity with rate r dot r cap plus r theta dot theta cap. Fine. So I'll do quickly. So here basically I get r double dot. Hope you can understand again with this r double dot means what? It is basically double derivative of r. We also write sometimes d square r by dt square. We can also write it like this: d square r by dt square. So that basically for saving some extra notations, I'm preferring to write it like r double dot. Fine. So r double dot r cap plus of course r dot and dr cap, which is dt, and then again r dot theta cap plus r theta double dot theta cap plus what do I get now? R theta dot d theta cap over dt. Interesting. So hope it is very easy for you to understand that we have done nothing but expanded the differentiation over all the parameters available. So we know already that theta cap is also depending upon time. We can see from the expressions as well. The theta is depending upon time, so theta cap also has to depend upon time. So now I have one new thing coming here, d theta cap over dt. So I can now differentiate this to obtain that particular unknown rate of theta cap. So if I differentiate it, what do I get? I am willing to save my step. So differentiation of sin theta will give you the cos theta, which is already coming in the r cap. So differentiation of cos theta will give you the minus sin theta, which is already coming here as sin theta. So I can quickly see that d theta cap over dt is nothing but minus of r cap. Minus of r cap, sorry, with theta dot. It is with minus of r cap with theta dot. Fine. So now I am going to use it here for basically summarizing the expression. Okay, and we know already this dr cap over dt, it is theta dot theta cap. It is theta dot theta cap. Theta dot theta cap. We obtained it earlier. R dot theta cap plus r theta double dot theta cap plus r with minus sign. Now it has to be modified. So I have to remove it. It is with minus sign r theta dot square and of course with r cap. So very easy and very much very interesting, because again I can see this whole acceleration of this so-called particle P moving in a two-dimensional plane with plane polar system is now having some component falling with r cap, some component falling with theta cap. So let us collect these terms. So let me have one parenthesis which I'll be dedicating to r cap. So with the r cap I have this, okay. What else I have? Yeah, okay, fine. R theta naught square with r cap. Nice. Fine. So with the theta cap, we again have some parentheses. Okay, this is the double of the quantity. So 2r dot theta dot and plus r theta double dot. Fine. So r theta double dot I have, and also I have 2r dot theta dot falling with theta cap. Very nice. Let me keep this highlighted. So the two typical expressions you have got for this new plane polar system, where what is happening, you have velocity having radial part as well as tangential part, having acceleration, radial part and tangential part both. Now I would like to give you one example which is in the real life. So basically, other than these two expressions, now I will not be needing all of these remaining, and I need some for solving some examples also. So I'm just removing it. Okay. Now I am ready here with the velocity and acceleration expressions. Now I would like to give a very interesting example. I hope you appreciate it. Uh, this is some car which is moving on a smooth road. Fine. So what is happening? It's very smooth road. You are enjoying this ride. You don't feel any jerk. You only feel moving in a particular direction. So of course you are enjoying nothing but the tangential part. You are enjoying nothing but the tangential part. You don't find a jerk. You find yourself propagated in a particular direction. So you are only experiencing the tangential part. How do we relate? Let me have particle P not going radially anywhere. Let me have particle P not going radially anywhere, but going tangentially. Very popular, the motion in the circular motion. So how do I modify it? Not going radially anywhere means r dot 0, but tangentially, of course, theta dot is not 0. So what do I get with my velocity? R theta dot theta cap. Fine. Have you seen this velocity somewhere? Hope you recall from your school. Yes. So studying circular motion, the velocity which you have seen always for solving some trivial problems, all that velocity is nothing but the tangential velocity. So popularly you have also used sometimes this theta dot written as omega. So you have been using this as v is equal to r omega. So omega is nothing but theta dot, the tangential velocity. So what would happen now if I don't keep getting this smooth ride? I get a jerk somewhere. I get a rumble strip, or may I get I may get some pit. So immediately my car is coming and falling into this pit. So as it is falling into this pit, what is happening? Am I only getting the tangential motion? No. the access force has to be immediately given to the center. As force is given to the center, means radially I should be in a position to receive this force. I get a jerk. I get a jerk. So R dot for this so one case is not zero, and of course I'll be handling with radial part also in those problems. So whenever I'm getting some bit or maybe I'm getting some rumble strip, so in both of these possibilities, what is happening? I may have R dot falling zero for the smooth journey. I may not have this R dot falling zero for whenever I'm getting some change around the center. So this is how we should be ready to handle the examples, keeping acceleration and velocity expressions ready with us. So now immediately I start solving the 2-3 examples.